But we're going to start with Andrew Sengul, who's made a bit of a splash in the APL community with the entertaining April compiler. And I think I also want to point out that he's contributed to the conspiracy theory that Common Lispers and Scheme programmers are all like closeted APL programmers. So,
thank you, Aaron. And thanks to everyone for hosting me here today. I'm Andrew Sengul, and I'm presenting Faster APL with Lazy Extensions. This paper chronicles recent developments in April, my compiler for the APL language. The project, in this case, was to add elements of deferred evaluation to the April compiler, and in so doing, to optimize better the code that it produces. April is written in Common Lisp, a language some of whose features I'll be exploring today. The results of this project were a new edition of the April APL compiler with a multifaceted framework for optimization, choosing the best available method to optimize whatever is being evaluated, falling back on slower methods when faster methods don't work. In some cases, the performance I achieved was better than any of the tested APL variants, so we'll be exploring how that happened. At this point, let's go back to the beginnings of April. The April project began in 2017. I was investigating possibilities for compiled APL. It had been said in some quarters that compiling APL wasn't possible. I wanted to test whether that was the case. I also wanted to bring some more powerful array tools to Common Lisp. Common Lisp has quite good array features, but the syntax for interacting with those can be cumbersome. And April has always had a focus on interoperability and easily interfacing with outside systems. So why Common Lisp? As I mentioned, almost all of the array features that you need for APL are built into Common Lisp. It allows nested arrays, supports ranks from 0 up to 255 in most current builds, even more if you use a custom build. And the Lisp macros allow for an elegant way of specifying a language. And because of this, April's compiled output is easily human readable and also easy to process. And the interactive development supported by Lisp makes it quick to create and bug test features. Some more on April's technology. The language is built around a specification that you can find in the spec.lisp file in the main repository. This spec sets all of the function and operator glyphs alongside their tests. And it also designates the utility functions and other properties of the language. For example, the function that's used to filter out comments from code is linked from this spec. The spec makes the language easy to extend. You can create what are essentially patches on the core April language in the same format of the spec. Therefore, you could distribute sublanguages that function by simply extending the main language. April can be used within CL by using the April form, April in parentheses, and there's also an Emacs mode that I've written which gives you a REPL for a more traditional APL experience. Some people have also developed some experimental console interfaces for the console REPL experience. Here's an example of APL code and its compiled equivalent. This is passing the compile only option, and this APL code transforms into this. The actual working part of this starts with this A call. You can see how this is the slash, the row iota is here. So this APL code is expressed in this way in Lisp. The design of this code can be seen to mirror the design of this chip. This EEPROM chip has a core module which is dwarfed by the framework used to integrate it with the rest of the system. And the design philosophy of April mirrors this to a degree. Now let's talk about some of the historic parallels between APL and Lisp. Both languages were invented for use as mathematical notation before anyone considered implementing them on a computer. APL, invented by Ken Iverson, and Lisp by John McCarthy, both didn't envision these languages being evaluated on computer until their students and colleagues wrote the first implementations. There's also been some ongoing parallelism between APL and Lisp in terms of their feature set. APL is mentioned several times in Common Lisp, the language, by Guy Steele. And there's some of Lisp's math functions were transcribed from APL. Both languages rose to prominence on mainframes. They served as essentially a complete operating system environment on these machines. And APL famously on the IBM System 360, and for Lisp, there was a line of Lisp machines designed specifically for the needs of the language. The interactive development experience these languages provided required the resources of a mainframe in those days. And when the microcomputer revolution happened, APL and Lisp were kind of left behind. Those computers obviously needed the most expedient form of programming possible. However, the lessons of Lisp and APL have been relearned over and over by other languages, porting in parts of APL and Lisp ever since. You can see some APL lineage in languages like R and Julia and even the GLSL for graphics. And Lisp's MapReduce and closures have appeared in many other places. The K language, in fact, is a descendant of both. And talking about April compared to other APLs, some K features have been ported in. For example, K's if statement syntax, the $ bracket notation. This allows you to create multiple nested if-else statements along with multiple statements inside a clause. This is compared to APL's conditional guard syntax. The guards only allow you to have multiple statements in the final clause. So that's an improvement for if-else. It also supports n-argument functions as seen in K. Using this bracket notation, you can pass any number of arguments into a function and then associate them with arbitrary symbol names. This does disallow the use of traditional APL operators, so you should keep that in mind if you want to do an n-argument function. And then April's workspaces are actually Common Lisp packages under the hood. So they work a bit different from traditional workspaces. You can essentially deploy libraries as an April workspace and then import their functions and values in your working workspace. As far as user experience goes, April is it's more in line with mainstream languages than other APLs in that it tends to store its code in source files. So you're typically writing APL source into files and then loading them, as opposed to the traditional APL experience, which is actually to embed a line editor in the REPL for a fully REPL-driven experience, harkening back to the mainframe days. April's core library is limited. It's got basically the lexical functions and operators in APL and a few quad functions, but you can very easily import Common Lisp functions. In fact, on 2 occasions I'm aware of, different April developers have ported in a tool for running shell commands into April. This only took about 5 lines of Common Lisp. And of course, the interactive development is in keeping with both CL and APL traditions, but there's a different form of, but it's a different experience doing it in a CL REPL with April. At this point, the question arose, what more can April bring to the programming field? I had my APL compiler interacting with Common Lisp. It was processing arrays, but what more could it do that other systems weren't offering? My answer to this was virtual arrays. The virtual array model for April is based on thunks, that is, tokens that represent computation that's yet to be performed. With thunks, it creates many opportunities to avoid unneeded computation. You can do loop fusion and other processes to skip memory writes, cache accesses, and combine multiple computations into a single one. You can cut down on a lot of round trips between CPU and memory this way. And these can be considered elements of lazy evaluation. April is not strictly lazily evaluated in the sense of languages like Haskell, which have a more all-encompassing approach. But we'll talk about that momentarily. And in April, you can even do things that would otherwise be impossible or highly impractical in other languages. In this code string here, for example, I'm creating a 2 million by 2 million square matrix. That's 4 quadrillion elements, doing some processing to it, and then taking its upper left 5 by 5 submatrix to return. April will return the result of this in under a millisecond, because all it actually does is solve for the 25 output elements. These massive input objects exist only in theory. Only the 25 output elements are accounted for. The road to developing this involved a significant change in philosophy in April. Originally, April didn't use a lot of object-oriented programming. There was one class that expressed the language's core idiom within my system. But to make the thunks work, I made a big switch, and CLO and Common Lisp object system classes were created for each of the functions and operators. So the APL macros and the central spec used by April made this changeover relatively smooth. I was essentially able to rebuild them piecemeal, and anytime something received a thunk that didn't know how to deal with it, it was rendered and written to memory. More about April's evaluation model. When you evaluate an APL expression with April, it produces a tree of these virtual array objects. And these objects have a method called render, which is used to write the array into memory. This rendering doesn't happen until necessary, but what exactly does that mean? There are some APL functions, like without and union, that have to render their input, because neither the shape or the content of their output can be known until they calculate for each element. So in these cases, adding one of these functions forces rendering to happen at the point where it occurs. Arrays also have to be rendered naturally when they're passed out of April, unless the user opts to receive unaltered thunk objects, unaltered virtual arrays. But at the same time, a virtual array's shape can sometimes be found without doing any rendering. For instance, if I was to put a row here in front of this expression, it would look at the next object, see that its shape is 5, 5, and return that, and none of the ensuing material would ever be touched. So in some cases, it can eliminate quite a bit of computation. More about April's model. The virtual arrays fall into two main types, primal and derived arrays. A derived array is a virtual array that derives from some other object, an example being 3 rotate A. This outputs a virtual array that's defined as the array A rotated by 3 elements along its last axis. A primal array, on the other hand, doesn't have a base array. Its content is determined entirely by parameters that it receives. So the monadic iota produces primal arrays, iota 9, iota 4, 5. Those are 2 different primal arrays. Also, 20 take neg 5 take 1. These are examples of expressions producing primal arrays. That last one is special. We'll talk a bit more about it later. An important concept to understand for derived arrays is that of a base. All derived arrays have a base property. The base is the thing that they are deriving from. Oftentimes you'll have a derived array which has a base that is another derived array which has a base, and these linked together structures form an entire tree of virtual array objects. And many of the methods of these objects involve traversing up and down that tree to collect pieces of information needed to render them. Here is an example. This is a simple virtual array structure, not a tree really, just a chain. The matrix M is the actual matrix written in memory, and 3 steps of transformation are performed on it. The Vader turn, the Vader section, the Vader expand. These are the class names of virtual array classes. So all the derived array classes start with Vader, standing for virtual array derived. Primal array names start with Vapri, virtual array primal. Here's a more sophisticated example. This is a tree structure. So here you have a catenate, which is taking 3 arrays and gluing them together. So that's catenate reduce, ABC. And then 3 more steps of transformation are performed on it. And you can see section 2 of the paper for these figures and more information about them and all their properties. That's not where the challenges end. funcs are not always the most efficient way to represent a computation. Let's take Conway's game of life. This is a classic APL function. When you run this iteratively and you're only producing virtual arrays, its output will grow exponentially. So how can you avoid this kind of runaway growth? I set 3 rules for automatic rendering of arrays. When an array is assigned, it gets rendered. Here you see the A gets this expression. This will be rendered, written in memory, when it's assigned to A. They are also assigned when they are passed to a user-defined function, a defun. This 100-element vector will be rendered when it's passed to this function. However, both of these cases can be manually overridden by a programmer. And the key to that is using the bow tie syntax with this little expression here. I'll get into some more of that later, and you can read all the details in paper section 6.3 and 6.4. Now, there are 2 major phases to the rendering process. Those are shaping and generating. The process of shaping is finding the shape of an output array. The process of generating is actually fetching each of the elements from the input array or arrays and then placing them in the output. So here I'm going to talk about approaches to generating. Shaping is pretty quick no matter how you do it because the complexity only grows with the rank of arrays, but indexing or generating grows with the size of output. So that's the more complicated one to deal with. The simplest way is called row major indexing using generator functions. That's when you have a function that takes a row major index and returns a value that exists at that index. So the way that you populate the output is you call the functions in a chain, going from the output to the input, returning back the input element from function to function. This is a simple technique. It applies to arrays of any rank and shape, but it's also very slow. You have to do stride encoding and decoding of indices at each step. However, this will serve as a fallback when other methods aren't available. You can see figure 3 in the paper for an example of this calculation. It's the line starting with R0 with RO gets. You can note that there are encode and decode functions happening at each step. That's expensive because that means division and multiplication. So how to avoid this? The next technique I developed is coordinate vector indexing. That means instead of handling row major indices, you perform a series of transformations on a Cartesian coordinate vector, going from the coordinates of the output array to the corresponding coordinates in the input. So you're not going to use a literal vector of these indices because that structure it has overhead to deal with. Instead, the way I do it is to encode the series of subscripts within a larger integer. And this approach, of course, is limited depending on the rank and shape of your array. For example, the coordinates 1, 2, 3 can be encoded in this 32-bit integer as this number. See, it's got the 1, 2, and 3 encoded in its bytes. This is provided, however, that the array's dimensions are all below 256, so that each index fits in a byte. And a system like this requires deferred evaluation because you have to know the maximum width of your indices across each transformation that occurs, not just at the end. And then how do you actually do this coordinate vector processing? Here's a couple of options. The first that I developed was optimized Common Lisp functions for specific transformations and specific array properties. In this case, you can see that I've got these the statements and these declares. These establish the type of integer that's being processed by this function. In this case, this is a function for handling the rotate transformation along the second dimension of an array whose elements are whose indices can be expressed in 1 byte with a rank of 4 or below, meaning that they fit inside a 32-bit integer. So using Common Lisp macros, I was able to exhaustively generate a set of functions for all the currently supportable array ranks, shapes, and so on. In this case, see this byte 88? That's me addressing the second byte, 8 bits, offset 8 bits from the beginning of the integer. The second method I developed is generating actual assembly language kernels. This Lisp form is this Lisp form is transformed by a Common Lisp-based assembler into these assembly instructions. And these kernels are implementing specific actual transformations. In this case, it's a 12 rotate A, where A's final dimension is 40 units. So you see I add 12 to the lower byte of this register. I compare the lower byte to 40. If it's lower, I jump to complete. Otherwise, I subtract 40. So that implements the changing of the index in accordance with this rotation. A word on performance. After having built this, I ran a series of benchmarks. These were taken using a March 2023 build of April. The April A refers to tests done using April's assembling effectors. That's the assembly kernel system I just showed you. And the April I uses coordinate vector indexers. That's this kind of optimized function, not specific to an individual transformation. So I used 3 different computers for this test. There's these 2 are desktop workstations running AMD and Intel chips, and then this is a server instance with 2 cores. These are 48 core processors for 192 threads total on this system. So we see how they stack up. In most cases, the April A is faster than the others by a significant margin. Notably, on the server, it's actually slower than Dialog in this case. This is because, I suspect this is because it's splitting this relatively small operation across 192 threads. Some thread throttling in this case would probably improve the performance, but once the size of the operation becomes larger, April A really comes into its own. So at first I tested with a 200 cube array. Next, I tried a matrix, 10,000 by 10,000. Here again, April A is pulling ahead. And finally, I tried a 4-dimensional array, 200 in each dimension. And with this large array, April A really comes into its own, and we can see the biggest deltas. Interestingly, the Intel processor for most operations is consistently slower than the AMD. I investigated and found that that was down to memory bandwidth. And you can see that the memory bandwidth has the same effect across both April and Dialog. This material is also, it's in section 7 of the paper with some further discussion. Then having done this, the discussion of efficiency so far has gone down to the lowest levels of programming, down to tuning assembly kernels 1 instruction at a time. But there are more benefits to be realized by climbing up the ladder of abstraction. The Common Lisp object system has many tools for expressing customized behavior of objects depending on their specific properties. And using these kinds of combinatorics, you can skip a lot of computation steps before any indexing or generating functions are called. For example, you can condense multiple rotations, you can condense successive takes and drops. Also, if you recall, I talked about that 20 take, neg5 take 1. That's producing a primal array. In this case, it produces a one-hot vector. And one-hot vectors are an important type for machine learning. It's a binary vector with a single 1 and the rest of the elements being 0. It's easy to sparsely represent. All you need to know is the length of the vector and the index of the 1 value. But a lot of conversations in APL around machine learning have mentioned that it's hard to express this kind of sparse type in APL. It's not really part of the paradigm. And that's a roadblock between APL and machine learning. But in the case of this virtual array system, it makes it straightforward to emit this kind of object. And another demonstration, this is a Mandelbrot set explorer written in 3 lines of APL. You'll notice that this value C, this is a virtual array expressing a vector of matrices, different levels of magnification of the Mandelbrot set. If you were to write this the last matrix in the vector into memory, it would require about 16 quetabytes. And quetabyte, that's 10 to the 30th power bytes. That is fortunately not required because this bow tie expression in front of the C value determines that it will be stored as a virtual array and not rendered. The only part of C that actually gets rendered is the slice that you choose to display. And the Common Lisp code up here is writing the returned data in the form of a PNG file, demonstrating the usefulness of merging these two languages. So to wrap things up, my goal of a faster APL implementation was realized. I created a framework for array processing where you can choose the fastest method of doing a given operation, and the slower methods act as fallbacks when the faster ones aren't applicable. And the automatic rendering behavior means that April developers don't even need to know how the system works. They can write in a traditionally eager style, and it will work. Once they start learning about the lazy features, they can begin to incorporate those using notation like that bow tie to avoid rendering when it's not necessary. Then what's yet to come is that there's still obviously quite a bit of optimization left to be done. I've really just scratched the surface. Among other things, I'll be optimizing arithmetic. There have been lots of arithmetic optimizations in array processing, so that wasn't my priority. My priority was getting some of the reshaping stuff done. And then having generated x86 assembly kernels, the logical next step is to expand other architectures. The most interesting of these being GPUs, because that opens the way to machine learning applications. And then that's not the only application of April so far. April has been used in a hardware startup called Bloxel. And let's play this. Is it going to play? So Bloxel is what we call a luminous structural display. Bloxel is a material that is the common square translucent blocks that we've all seen in windows and bathrooms. They have LEDs placed inside them, and each block functions as a pixel. That means that you can, here we go. That means that the individual blocks form part of an animated image. So you can build with this material, and it also functions as a light source and a display. Building material, light source, and display, this is the only product we know of that fills all three of these roles. So this is Bloxel, repeated over and over again. We also did some DJ streams, live streams, incorporating the Bloxel. And we also used it to implement a game you may have seen before where you control falling blocks and fill up an area and clear lines. But that video isn't available to us at this time. But with that said, I would like to open the floor to questions.
Hi, thanks. I have some familiarity with these kinds of systems that represent some computations as delayed. And the usual problem is that you change your program a little bit and then it has to render or manifest the array in memory, and then your program blows up because you're working with a 4 quadrillion element array. So you have these very, very specific rules about it will definitely render the array when you're binding it to a variable or applying it to a user-defined function. Mm-hmm. But what about the other built-ins? APL has lots of those, like when you're filtering and such. I mean, do I just need to memorize a whole bunch of rules about what's safe to do with my delayed arrays?
Right now, it basically applies the most conservative method for rendering when no other behavior has been specified. So for something like filtering, like the without function, it will force render in that situation. So when if you're developing something with a really large virtual array, you may run into situations where it'll suddenly force render. And I've had some amusing error messages like, you have attempted to allocate 8 petabytes of memory, but only 11 gigs more are available. So that is a gotcha, but the alternative is that you just can't express any really large array in APL.
So, I have a follow-up if that's okay. So for filtering, you could kind of imagine a delayed representation where you can just ask it for the next element and it will give you the index of the next element instead of just the value. So that would not be parallel, of course, but then you could actually fit. So would that be a reasonable trade-off? Can you think of a way to integrate that? I think that's called a push array in the literature, whereas what you have is what's called a pull array.
Yeah, it's an interesting concept. It's not an area I've delved into. My focus at this point, has been on heavily optimizing the reshaping functions. So that'll be a bridge to cross when I get there.
Hi, thank you very much for the talk. I'm not very familiar with this array work, but I thought it was very interesting. So I have two questions about the benchmarks, which I didn't quite understand. One, you said it was memory bound. Is that really the most interesting type of benchmark? Would you not be interested in the compute limit of your implementation? You said different processors behave differently because it was memory bound. The memory access was the limiting factor. And my understanding
it wasn't the limiting factor. It was the determining factor in the difference between the Intel and AMD chips on the desktop.
Okay.
So did.
Okay. Yeah, but then it's bound by that, right? Then the memory was the limit. It's not there's memory limit, compute limit.
Their numbers of CPUs are almost the same.
Okay.
It's a 12-core chip versus a 14-core. So 24 versus 28 threads.
I think I can answer to that a little bit.
Yeah.
Which is in APL, the reshaping operations are almost all reordering operations, so they're almost entirely memory bound.
Okay. No,
So a lot of these operations are specifically memory bound operations. We're trying to reduce the memory, the bandwidth pressure on them.
okay, thank you. That answers my question.
Aaron was saying that these reshaping operations in APL are almost all memory bound to begin with.
Okay. And how would that compare to like a C implementation of equivalent of that does the same thing? Like did you compare across the bridge to the more traditional, or maybe your approach is more traditional, but like a C or Rust implementation, and they do lazy evaluation also and vectorization, which is something I'm not sure you can do as easily?
The C approach to manually writing this kind of thing will be faster than the APL because you can manually loop. This, if it's been coded correctly, it will be around the same as that C, because it creates these kernels that absolutely minimize cache access, even movement of data between registers. So if the C is compiled as well as it can be, and I'm not experiencing any unforeseen problems in my kernel implementation, they'll be approaching the same speed.
Okay, but you haven't tested it.
I haven't tested that with handwritten C yet. Obviously writing C for each of these cases will be a significant amount of time.
So this idea of integrating APL in a language seems very nice that you can do that. But if you're not really a Lisp programmer, you might want to do it from within Python or some other language of choice. How easy would it be to kind of use your work in those settings?
If you're not a Lisp developer, so currently, April began, the early use case was basically working with it from within Common Lisp. Since then, I created the Emacs mode for April, where you can interact with it without seeing any of the Common Lisp. And there's some plans in the works for other sorts of interface that obscure the Common Lisp. And in this case, the Common Lisp can be used as a configuration language where you create the sort of the substrate beneath your APL interface. For example, let's say that you wanted to create an Emacs workflow where in one panel you were working on APL code, and then in the other panel are images that you're generating by writing those pieces of APL code. The way that the code generates the images and the association between them, that would be defined in the underlying Common Lisp. Once that's defined, once that substrate is created, users can work on top of it without seeing the Common Lisp underneath. So it's basically forming a control language for the process underlying the interface. Does that make sense?
Sure. I'm just thinking, I think I really like the idea of having APL as a kind of an expression language within some other language. So I guess there are some ideas that you can really take from your work and then redo in other contexts. So this is what I kind of, it's a little bit difficult to take the whole
yeah, and Common Lisp has a good deal of support for interfacing with other languages. So I know a couple friends have done Java and Python link-ins, so could potentially give access to APL within those languages.
All right. Did you have a question? Or? Okay. We should probably make sure everybody gets in time for lunch. We should probably get going.
All right, thanks very much, everyone.